Hey folks, this is Captain Jones here to talk to you about hardwired versus microprogrammed FSMs. So this is going to be a slightly different take on finite state machines than we've seen in EE360, and it'll be the kind of finite state machine that we use to power the control unit in the LC3. So today our objectives are twofold: to sort of introduce to you how these two finite state machines operate, specifically the microprogrammed, and then on top of that we're going to add something called a sequencer. And then hopefully by the end of this lesson, you can kind of compare and contrast the different types of finite state machines that we're going to look at today. So let's get started. To begin, I've got sort of three separate things we're going to take a look at here. We're going to start with a look at a finite state machine that might simulate a really simple traffic light. Right? So I've got green, yellow, red lights. I'm going to assume the inputs to my finite state machine are three buttons. One is a pedestrian crossing button that a pedestrian can press to say that they want to cross the intersection. I have a sensor in the road to detect when there's a car present. And then lastly, I have an internal timer that can sort of alert my finite state machine to a specific timeout period. So this little state diagram is depicting how those sensors might interact with the lights to create this little intersection light. And we're going to assume that we're going to give some precedence to the pedestrians. So to start with, the default is green here, and as long as there are no pedestrians, then our traffic light stays green. As soon as that pedestrian crossing button is pressed, our finite state machine transitions to yellow and then automatically to red, and it will stay here until the timer is expired and there's a car present. So at a minimum, it stays red for the timing period. If there are no other cars, then even after the timer's expired, the light will stay red until a car shows up, and then it'll go back to being green to allow some cars to pass. But as soon as someone presses that button again from the green signal, we go back to yellow and then red. Okay, here's a sort of a hardwired implementation of that. And by hardwired, I mean we are building a specific circuit that once it's built, it cannot be changed to perform this exact function. And so this is using that LogicSim simulator. If you put this in there, then you'll see the green, yellow, red lights kind of functioning the way we have described in our finite state machine. So one difference that we can maybe employ is to use something called a microprogrammed finite state machine. And the microprogrammed finite state machine looks like this. I have a register here that holds my current state, CS. And then the whole finite state machine is encoded basically in this a chunk of memory. And I use the current state of my finite state machine and whatever my inputs are as basically the address in memory that I'm using to look up what should be my next state here, NS. And so you can see an example of that here in this diagram. So for instance, if I'm in state, if I'm in state 01, then that corresponds to the yellow state. Regardless really of my inputs, I should transition next to the state 10. So you can see here these first four rows, right? Regardless of what these inputs are, pedestrian button, timer expired, car present, my next state is always 10. And so if the current state is 01, if my inputs are 100, then the output of this memory, the next state is 10. That's what goes here into the register on the next clock cycle. And then, I might have some combinational logic here to sort of, specify what my outputs are based on the current state. But, in some iterations, I could actually fold that into the memory if I wanted to. And so kind of the neat part about the microprogrammed memory is that I can encode. This is basically when I program the memory, I'm programming the whole state table, into the memory. So every transition is encoded, as zeros and ones, and so let's say, for instance, I wanted to change my my state diagram a little bit. Let's say I didn't want to give the precedence to the pedestrians; I wanted to give the precedence to the cars. So in this state diagram, you can see that I don't just transition from green to yellow as soon as the pedestrian button is pressed. I only make that transition when the pedestrian button is pressed and there are no cars present. So I'm giving precedence to the cars. The light will stay green as long as there's a car there, even if a pedestrian is waiting to cross. It's only when the cars go by and there's no car present and the button's being pressed that I make that transition to yellow and then to red. And then also when I'm in this red state, I don't stay here once the timer's expired if there are no cars present, regardless of whether the cars are present or not. Once the timer's expired, I go back to being green to allow potentially some cars to pass. So this is a slightly different take on this finite state machine that uses the same inputs and the same outputs in just a slightly different way. If I was going to sort of change up my hardwired circuit to be able to implement this new state diagram, I'd have to completely change the whole circuit, which, if I'm going through many changes, different iterations of my design, that might be, a bit onerous. If I'm using a micro-programmed state machine, though, the hardware doesn't change at all. To implement this new finite state machine, this new state diagram, all I need to do is basically reprogram my memory. So you can see here now. Let's take this third row. If I'm in state 1, 0, so that's the red state, and then as soon as that timer is expired, I make my transition back to the green state 0, 0, and so I can, with one circuit, I can encode many different types of state machines using this memory as to sort of a way to sort of encode my state table. Now, one downside to the microprogram memory is that regardless of whether a state transition kind of makes sense or not, I have to enumerate every possible combination of current state and next state. This memory is in this case has to be 2 to the 5th tall because I have 5 different bits for my inputs and my current states. For certain finite state machines, like the LC3 is, we'll see next lesson, that can get really prohibitive, meaning that the memory would have to be massive. So one way to sort of keep the memory small but still leverage this ability to kind of reprogram stuff is to add something called a sequencer. So in this case, we're going to change up our memory slightly so that it's just the kind of the current state that addresses it. And my inputs are coming down here into this multiplexer. And so in my memory, I'm not just going to sort of list the next state. I'll list 2 next states. One if some condition is true, and one if some condition is false. And I'll also list sort of which condition I'm waiting on. So you can see here 3 bits are going into my multiplexer. I've got 3 bits here to specify which condition I'm waiting for. I can wait for the pedestrian button to be true or false, the timer expired to be true or false. I've also got a 0 or a 1 here to sort of indicate either a no transition or a always transition. So in this memory, I've got 7 bits here. 3 of them will specify, okay, which condition are we waiting on? Let's say we're waiting on the pedestrian button. The next 4 bits are going to specify, which next state to transition to if the condition is false, and which next state to transition to if the condition is true. And so the output of this multiplexer up here comes to this multiplexer that chooses which of those 2 next states. If the condition we're waiting on, hypothetically, the pedestrian button, if it's false, then we select this next state, meaning we don't take that branch. And if it's true, then we select the other next state. And whichever one is selected goes into the register, kind of like it did over here. So let's see, we'll take a look at an example. So for our first kind of finite state machine here, the only kind of slight weirdness about this specific sequencer is that we can't specify more than one condition. So this transition here out of our red state, timer expired and car present, we sort of have to separate into 2 transitions here where we sort of wait for first the timer to expire and then also the car present sensor to be true. But as long as we allow ourselves to do that, we can specify our entire finite state machine in this little sort of 4-row table. Basically, I only need 1 row in my memory for every transition I take. And so, in this case, I can significantly reduce the size of my memory from 32 rows down to 4. I need to make it a little bit wider to account for sort of the code in this sequencer, but it's a significantly smaller memory. And then additionally, with this finite state machine, it's not difficult to change it up to implement our alternative finite state machine. So this one that gets sort of a precedence to the cars. Similarly for the green state, we have to kind of break it up because we're waiting on 2 transitions. But if you break that up sort of like this, then effectively we have the same finite state machine, and I can reprogram that memory in my micro-programmed finite state machine to be able to implement that state table. So the micro-programmed state machines leverage some piece of memory that effectively encodes your state table. And the advantages it gives you are that you can reprogram that memory and implement a totally different finite state machine sort of at will. We're not required by, we're not restricted by whatever circuit we build. In order to make that memory a little more manageable and not so huge, especially when we get lots of inputs or lots of bits of state, then what we might do is add a sequencer. And so then the kind of basic format for that you can see in the table here is in each row of my memory, I'm going to specify which condition is the one that I'm potentially branching on, and which state do I branch to if it's true, and which state do I branch to if the condition is not true. And this becomes a very powerful finite state machine. You can encode a lot of different finite states, or a lot of different finite state machines using kind of this format here. And we'll see in really the next lesson how the LC3 uses a microprogrammed finite state machine with sequencer to manage the really large state machine that it takes to control the LC3 computer. All right, folks, that's all I got. I'll see you next time.